The AI industry is pouring capital into infrastructure faster than any technology cycle before it.
OpenAI has signed a $300 billion deal with Oracle for cloud computing power.
Google raises its capex forecast by $10 billion to $85 billion for this year.
Amazon pledging to spend $200 billion capital expenditures on AI infrastructure.
We've created a brand new industry called AI infrastructure.
And as that spending accelerates, one fear is getting harder to ignore.
AI bubble.
AI bubble.
AI bubble.
AI bubble.
Are we in an AI bubble?
Jeff Bezos has offered one of the more useful ways to think about that debate. At a tech conference last year, he argued that if AI is experiencing a bubble, it looks more like an industrial one than a purely financial one. A boom where investors can overpay, companies can fail, and yet the infrastructure left behind can still prove enormously valuable. His clearest example was the internet. Telecom companies spent aggressively on fiber optic networks in the late 1990s. Capacity ran far ahead of demand, many operators collapsed, and huge amounts of fiber sat unused. But the internet did not fail as a technology. Broadband, streaming, and cloud computing eventually filled that capacity. The long-term demand was real. The investment had simply arrived too early. Fiber made that mismatch survivable because it had one enormous advantage: time. Fiber optic cable could sit underground for decades and still be useful when the economics eventually caught up. But AI, however, is starting from a different place. Given how quickly usage and revenue are growing, there is little doubt about the long-term demand for AI. But the infrastructure being built to serve that demand operates on a very different economic clock. Today, compute is scarce and demand is running ahead of supply. The uncertainty is not whether customers want more AI. It is how long today's infrastructure can remain economically useful. Unlike fiber, which can remain useful for decades, an AI accelerator may only have a few years before newer hardware changes its economics, while the systems around it may need to be upgraded along with it. That compresses the earning window. So the real question is, can the AI build-out earn a return before the industry has to spend again? The answer to that depends on three tests. First, asset life. How long does each generation of infrastructure remain economically useful? Second, task economics. Can the revenue generated by AI tasks keep pace with the compute required to complete them? And third, physical delivery. Can the infrastructure arrive in time to earn a return? Each is a different way the timing of the AI investment cycle can break, even if the technology itself succeeds. Let's unpack this. Start with the first test, asset life. When a company buys an AI accelerator, it spreads the cost across the years it expects the equipment to remain useful. Buy a chip for $50,000 and depreciate it over 5 years, and the company records $10,000 of expense each year. The problem is that nobody agrees on the correct useful life. Microsoft now depreciates much of its server and networking equipment over 6 years, up from 4 under its previous estimate. Alphabet generally uses 6 years, while Meta recently extended most servers and network assets to 5.5. And Amazon's experience shows how quickly those assumptions can change. In 2024, it extended the expected life of its servers from 5 years to 6. A year later, it reversed part of that decision, shortening a subset of its servers and networking equipment back to 5 as AI development accelerated. That change increased Amazon's 2025 depreciation expense by $1.4 billion and reduced net income by $1 billion. It exposed the uncertainty underneath the numbers. If the equipment remains productive for 6 years, spreading the cost over 6 years is reasonable. If rapid improvements make operators replace it after 4, a longer depreciation schedule makes current profits look stronger while pushing more of the cost into the future. Michael Burry, the investor best known for betting against the U.S. housing market before the 2008 crisis, has made the most aggressive version of that argument. He claims that hyperscalers are depreciating computing equipment over 6 years, when its real useful life may be closer to 3. His estimate is probably too bearish, but the underlying question is valid because AI hardware is improving unusually quickly. In a power-constrained data center, operators care about useful compute per watt and rack space. If a new generation produces several times more output from the same footprint, continuing to run older chips carries a massive opportunity cost. This is where depreciation becomes a return on capital problem. A $50,000 accelerator spread over 5 years carries $10,000 of capital cost each year. If its economic life falls to 4 years, that rises to $12,500. The chip didn't get slower or more expensive, but it now has to generate far more revenue in less time just to break even, before accounting for power, cooling, or the building around it. Across a fleet of 100,000 accelerators, shortening the useful life adds hundreds of millions of dollars to the annual capital burden. And if the fleet is replaced sooner than expected, billions of dollars of the original investment may still remain on its books just as the operator begins paying for the next generation. This brings us back to the fiber build-out of the dot-com boom. Unlike fiber cables, which could sit underground for 25 years waiting for demand to catch up, AI hardware has a much shorter economic clock. The hyperscaler's defense is that older chips do not become worthless. They move into less demanding work: smaller models, fine-tuning, batch processing, and synthetic data generation. An AI fleet may therefore resemble an airline fleet. New aircraft handle the most demanding routes, while older planes remain profitable on less valuable ones. There's some support for that argument. Older NVIDIA chips, the A100, the H100, are still widely rented, and at prices high enough to imply a genuinely long useful life. But the current compute shortage makes that evidence difficult to interpret. Are older chips valuable because they are durably useful, or because customers will rent almost any available capacity? Nobody can yet fully separate those two explanations. And the chip is not the only asset that can age. Traditional cloud facilities were built to last around 20 years, with several generations of servers replaced inside them. But AI hardware is becoming harder to swap independently of the building around it. Each new generation demands more power per rack, denser networking, and increasingly liquid cooling. The chip, cooling loop, and electrical system increasingly have to be designed together as one machine. This means a facility can have enough total electricity on paper and still fail to deliver it where the next generation of racks actually needs it, because the power arrives in the wrong place at the wrong density through infrastructure designed for a different system entirely. Goldman calls facilities caught between hardware generations transitional AI data centers, buildings designed for one generation that may already be inadequate for the next. So the asset life test spans 2 layers. The first is the AI accelerator itself, how quickly it loses its economic advantage and needs to be replaced. The second is the surrounding infrastructure, how quickly the systems supporting the accelerator cluster become inadequate and require upgrading. Together, they set the length of the earning window, how much time each generation of AI infrastructure has to recover its cost before the industry has to spend again. By the way, if you want to understand how the AI boom is changing the economics of infrastructure, that is what we cover every week in our newsletter, ARPU. Not just the models and chips, but the depreciation cycles, supply constraints, and companies carrying the cost of the build-out. To get that analysis in your inbox, the link is at the top of the description. The next issue is how quickly that infrastructure can earn back its cost. And here, the AI boom presents a paradox. The infrastructure can get busier without necessarily becoming more profitable. On the surface, the narrative around AI economics sounds overwhelmingly positive. According to industry data, the price of a single token, the basic unit used to measure AI usage, has fallen by more than 90% since 2023. Hardware companies expect that decline to continue. NVIDIA claims its next-generation Vera Rubin platform will reduce cost per token tenfold compared with Blackwell. Meanwhile, consumption is exploding. Tracking from Ramp shows that token usage among businesses grew 1,000% from January 2025 to April 2026. For anyone selling compute, that looks like a good outcome. Falling prices drive more usage keeps infrastructure busy, and total revenue can still rise. But token consumption is not the same thing as economic output. And that distinction is where the return calculation becomes complicated. Customers are not just buying tokens, they are paying for completed work, a bug fixed, a research report produced, or a customer request resolved. The relevant calculation, from the customer's perspective, is how many tokens are required to complete that work, and whether the price of the result supports the cost of producing it. Early generative AI was computationally more simple. A basic chatbot exchange might involve one prompt and one response, but the economic question was already difficult. Did that response create enough value to justify what the customer paid? The arrival of agentic AI further complicates that calculation, because a single useful outcome can now require far more computation. Ask an agent to research a topic, fix a bug, or resolve a customer issue, and it doesn't just generate text. It plans, searches, calls tools, checks its own output, and often retries when something fails. Each of those steps can require another model call, often carrying forward substantial context from everything that came before. Goldman Sachs suggests that turning a simple request into an agentic workflow can multiply token consumption by 10 to 50 times. Across the whole industry, Goldman projects total agentic token consumption rising 24-fold by 2030. Some workloads go much further. One 2026 study of agentic coding tasks found they consumed roughly 1,000 times more tokens than ordinary code chat. That increase in token volume can offset or even overwhelm the benefit of cheaper per-token pricing. If a token gets 10 times cheaper, but a task requires 100 times more tokens to complete, that task doesn't get cheaper, it gets 10 times more expensive. For an AI provider charging by usage, that can be good news. More computation can mean a larger bill. The question is whether the customer believes the completed task is valuable enough to keep paying it. Which of those forces ultimately wins? Falling cost per token, rising compute per task, and how much customers are willing to pay for the result is still one of the biggest unanswered questions in AI economics. Uber's experience offers an early glimpse of how that tension can play out in practice. In early 2026, the company burned through the entire annual budget it had allocated to Claude Code within just a few months as usage among its engineers surged. For the supplier, that is exactly what metered pricing is designed for. More usage produces more revenue. But for Uber, it pushed the economic question back onto the customer. On paper, Uber's adoption metrics looked extraordinary. AI was contributing to a growing share of engineering work. But Chief Operating Officer Andrew McDonald later admitted that it was difficult to draw a direct line to the company's surging AI tool usage and actual innovations served to consumers. Quote, "If you're not actually able to draw a direct line to how much useful features and functionality you're shipping to your users, that trade becomes harder to justify." End quote. Eventually, the customer still has to decide whether the outcome justifies the bill, and enterprises are increasingly refusing to pay for compute's sake. In recent months, Palantir CEO Alex Karp has made that point unusually explicit. He argues that businesses do not care how many tokens their employees consume, only whether those tokens improve a workflow or produce a measurable result. As he put it, enterprises may believe AI will create value, but they cannot have employees simply checking the weather with it or rearranging deck chairs on their personal Titanic. That ultimately sets a limit on how much AI spending any task can support. If the outcome becomes more valuable, customers may happily pay for more reasoning. If it does not, either usage, pricing, or supplier margins eventually have to adjust. This brings us back to the payback calculation. An AI accelerator has a limited window to recover its cost before newer hardware changes its economics. A $50,000 accelerator running near full capacity might look like a success, but if the compute required for each task rises faster than the revenue that task can support, utilization alone does not guarantee a fast enough return. That is the timing risk. The data center doesn't have to sit empty. It can run flat out right up until the next hardware cycle arrives, with part of the previous investment still unpaid. Suppose all that additional compute does create enough value to justify the spending. None of that matters if the infrastructure behind it cannot be delivered in time. This is where the economics collide with the physical world. Start with the queue. According to Lawrence Berkeley National Laboratory, more than 8,200 energy projects are currently sitting in U.S. interconnection queues, representing over 2,000 gigawatts of proposed generation and storage. For the projects that actually reached commercial operation in 2025, the median journey from interconnection request to operation exceeded 5 years. Most of what's in that queue never gets built at all. Berkeley Lab's own historical data shows that of the capacity that entered these queues between 2000 and 2020, only 13% had come online by the end of 2025. 75% had been withdrawn. A queue, in other words, is not a construction schedule. It is a field of competing proposals, and only a small fraction becomes usable power. But there is uncertainty on the other side of the connection, too. Grid operators are receiving enormous numbers of requests from proposed data centers without always knowing which projects are real, which have applied in several locations, and which will ever reach construction. PJM, the grid operator serving much of the eastern United States, has begun separating firm projects with concrete construction commitments from less certain proposals. Near-term projects without those commitments are now discounted in its forecasts, partly to avoid planning the grid around loads that may never appear. That leaves utilities and grid operators caught between two expensive mistakes. Build too slowly, and completed data centers may sit for years without power. Build too aggressively, and they risk building costly grid infrastructure for projects that never arrive, leaving other electricity customers to absorb part of the bill. Regulators are now trying to push that risk back towards the developers creating it. In June 2026, the Federal Energy Regulatory Commission ordered regional grid operators to examine new cost recovery agreements for large loads. The basic principle is simple. If infrastructure is built for a data center, and that data center never arrives, existing households and businesses should not be left paying the bill. That could mean larger deposits, firmer contracts, and longer-term payment commitments before utilities agree to reserve capacity or begin major upgrades. It may improve the quality of the queue, but it also raises the cost of securing power years before a data center can begin earning revenue. And even projects that clear these planning hurdles face a second weight: the physical equipment needed to move the electricity. Power transformers now carry lead times around 128 weeks. Generator step-up units run close to 144 weeks, nearly 3 years. Some categories of high-voltage switchgear are booking years in advance. None of that moves faster no matter how much capital gets thrown at it, because the constraint isn't money. It's how many transformers a handful of factories can physically manufacture in a year. Satya Nadella described the consequence in unusually blunt terms. Microsoft could obtain the GPUs. What it lacked were warm shells to plug into. Developers have an obvious workaround. Build your own power instead of waiting for the grid. Skip the queue, place a gas turbine beside the data center, and generate electricity on site. Except the turbine business is backlogged too. GE Vernova reported 116 gigawatts of gas power equipment backlog and reserved manufacturing slots in the second quarter of 2026, against annual turbine output of roughly 20 gigawatts. The company expects to expand that output, but only gradually, to 24 gigawatts in 2028 and 30 gigawatts by 2030. Developers racing to escape the grid queue are discovering they've just joined a different one. There are only so many factories on Earth that build these turbines, and every hyperscaler on the planet is trying to get in line at once. This is the pattern running through the entire build-out. Relieving one bottleneck often exposes the next. Route around the grid and you hit the turbine backlog. Secure the turbine and you still need fuel, electrical equipment, permits, and construction crews. If you've watched our episode on Meta's AI data center, you've already seen what that looks like on the ground. Gas turbines, hundreds of miles of new transmission line, a rural community in Louisiana absorbing 5,000 workers almost overnight just to get one data center powered. The result is that every component moves on a different clock. Chips can be delivered in months, a data center shell may take a year or two, grid power can take 5 years or more. And when those schedules fall out of sequence, capital begins sitting idle. Chips arrive before the building is ready, buildings finish before the power connection does, and by the time electricity finally reaches the site, a newer generation of hardware may require different rack densities, cooling systems, or electrical layouts. That is where delay becomes investment risk. A project earns nothing while it waits for power, but its costs do not stop. Interest accumulates, contractors and equipment become more expensive, revenue is pushed further into the future. Meanwhile, the technology the facility was designed to support keeps advancing. Each year of delay pushes the break-even point further away while bringing the original design closer to obsolescence. So the danger is larger than capacity arriving late. By the time the project comes online, higher costs, deferred revenue, and changing hardware requirements may have already broken the return calculation that justified it in the first place. So, where does that leave us? The strange thing about the AI build-out is that almost every signal can look bullish at the same time. Demand can exceed supply, data centers can run full, revenue can keep growing, and the investment cycle can still become harder to finance. In a recent interview, Jamie Dimon summed up that tension well.
When I look at AI itself, the amount of money being spent is huge. Will it in total pay off? Probably, just like the internet did. Will it pay off the way you expect and the timetable you expect? Definitely not.
AI can create enormous value, but the question is whether that value arrives fast enough to keep pace with the replacement cycle underneath it. And if you want to follow what happens next, where AI demand turns into durable economics, who captures the value and who is left carrying the cost of the build-out, that is what we cover every week in our newsletter, ARPU. To get that analysis in your inbox, subscribe at the link in the description. Thanks for watching.